Hello everybody, welcome to episode 28 of the video series in which we program an entire video game from scratch in the C programming language. Alright, episode 28. So last time we were working on making our little menu fade system, and I'll give you, let's see what that looks like. Draw a title screen. So since we left off last time, I have improved this just ever so slightly. In that, oh sorry, it was draw opening splash screen is what I'm talking about. There we go. I improved it ever so slightly. Remember where we left off last time? I had sort of like this brightness modifier variable, and then every so often it would decrement that brightness modifier, and then when you went here, instead of just having a constant a pointer to a constant pixel that just has this constant value in here, I had the pixel minus brightness modifier in here, right? If you remember that, I had a brightness modifier in there. And when that happened, the code worked okay. But what happened is it generated a compiler warning. And the compiler warning was right here. C4204, non-standard extension used, non-constant aggregate initializer. And I didn't like that. So luckily, it's really easy to get rid of. You get rid of it simply by not using non-constant aggregate initializers. But it's documented very well too, that error. That particular error says, with Microsoft extensions, you can initialize aggregate types with values that are not constants. Such initializations are invalid under ANSI compatibility. And that's a big red flag to me, because I want this code to be portable, and I want this code to be easily adaptable to other platforms. If in the future we want to port this game to something other than Windows, we don't want to be stuck using Microsoft extensions. So essentially, I got rid of it by making a new static pixel that starts off as just regular white, and then at certain points during the playing of the splash screen, it just gets darker and darker. And then eventually at 240 frames in, we transition to the title screen. I'll go ahead and show you what that looks like. So you have sort of that fade out effect there. Okay, and that works fine, and no compiler warning. So let's move on to now the next thing we want to do is I want to move on to the draw title screen, and I want to do the same thing here, only in reverse. Because I want the title screen to fade in the same way that the splash screen faded out. And when I started thinking about this, it got me into this sort of mindset where I was thinking how we've been using memset at the beginning of all of these scene transitions. I mean, we've been using this memset to clear the back buffer on every frame. Every time we start to draw a frame, we clear the screen to all black first before we ever start drawing it. And I started thinking, that made me think about the clear screen function, and how I could actually we spent a lot of time talking about SIMD and the clear screen function, and effectively we don't really need it. And the main reason for writing it was simply to introduce you to the concept of these SIMD intrinsics. However, even though this code works perfectly fine to clear the screen, it's not a very it's not really an effective use of SIMD. So I think the next time that we will probably cross paths with SIMD, and the only time that we'll probably use it in an effective way is if we go to alpha blending our our pixels together. SIMD is very good at that, and so and alpha blending, if you're not familiar, is if you can basically start to leverage the alpha channel in your 32-bit bitmaps, so where if you have, say, your alpha channel is 128, so that's 50%, and then you blit that over the top of another bitmap, then you'll be able to see 50% of it will come through. They'll blend together because the top image is only half transparent and half opaque, right? But here, this isn't really that necessary, and it really doesn't offer any speed advantages either, and I'll show you why. Why, given that we talked about these 256-bit registers and these 128-bit registers, why would that not offer us a speed improvement? Let's go back to draw title screen, which is, I really do need to start splitting these up into multiple C files because I'm starting to get lost in this list of functions. Draw, option screen, draw, title screen. Okay. And as you can see, I mean, our clear screen function using, again, the address of a M256, so basically a 256-bit buffer of all zeros, and of course I can run that and it'll run fine. Looks fine. But is it really any faster than just regular old memset? And you might be tempted to think, well, yes, the clear screen is going to be faster than the memset because the memset is only setting 1 byte at a time, right? And let me set a breakpoint right here. Right, run to cursor. All right, we hit the breakpoint. Let's go to disassembly and see what we see. Here's our memset right here. Let's see if we can step into, I guess it's F11. So the first thing I'm noticing here is that memset is already optimized to use SIMD, So there's no problem there. The second thing is that I was actually expecting to see, I'm not seeing something that I was expecting to see here, which I was expecting to see use of the store string instruction. And it might be in here if I continue following down through this assembly code. It might be. But essentially what I was looking for were the instructions. I was looking for the instructions repstos, which is store string. And I guess the rep is for repetitively, to do it repetitively, as many times as needed until you filled the buffer. And in fact, we might have something similar here. And that is a lot. That's a lot of code for memset. That's more than what I strictly would have thought was necessary. But anyway, let me go and show you something. Intel has a manual for their processors, and I believe this is it. And yes, it really is 5,000 pages. Alright, this is the Intel 64 and IA32 Architecture Software Developers Manuals. Combined volumes 1, 2A, 2B, 2C, 2D, 3A, 3B, 3C, 3D, and 4. So I'm not going to, like I said, this is 5,000 pages here of really awesome documentation that will tell you everything you want to know about about an Intel processor. But what I really wanted to look at was there we go. I just searched for the repstos instruction right there. And this is the key. This one sentence in this entire 5,000 page document is what I really wanted to draw your attention to. It says, also, note that a repstos instruction is the fastest way to initialize a large block of memory. There it is. So, as I was saying, you have store string. You also have store other things. There's a store W for store word. There's a store D for store D word. And so what that means is we can effectively replace this clear screen function. This clear screen function doesn't even really need to exist. We could actually not use that at all whatsoever. And instead, we could use this intrinsic right here, store SD, which is stores something D word, and then basically you supply. It's just like memset, right? Except instead of filling the back buffer with just a single byte, because remember that was the limitation of using memset, was that we could only store a single byte. We couldn't fill the back buffer with a pattern, and that meant that by using memset we could only clear the back buffer to some shade of gray, either white because that's all F's, or black because that's all zeros, or any shade of gray in between, because you could only type something like 7F, and then it would fill the entire buffer with 7F, 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 and effectively you would come out, the color you came out with was some sort of gray, like 50% gray. Now, with this function, store string or store SD, it allows us to store a D word. So it's essentially, now we're talking about like a pattern fill, because a D word is 4 bytes, right? Let's see. Yeah, so we need the destination, which we have, and then we need some sort of pixel. So this is going to be our pixel, which is conveniently, our pixel is 32 bits, right? So there's an all white pixel, and then we need a size, which since we're only going to need to repeat this, the same, instead of D word, I'll do pixel 32, right? It's the same size. So this should make my title screen all white, which I don't really want to do. So let's do something that actually demonstrates the concept I'm talking about. So let's do full blue, zero green, zero red, and full alpha. There we go. That made our title screen blue. And of course, the speed is going to be just as fast as any other function, because we literally just read in the Intel architecture manual, there's no way, you can't beat these. These are the fastest way to fill large chunks of memory. Alright, so what if so we can make this any color we want. Let's add a little bit of green in there. I guess this will be some sort of shade of cyan or something, turquoise, I don't know. Can't really tell a big difference. Let's add some red in there. Makes me wonder if I'm thinking about this correctly. That actually may be A for alpha. I don't know if this is ARGB or what. Let's do this. Let's turn this channel off and do this one. So this should be zero blue and full green and zero red and full alpha. Let's try that. No, see, I had it wrong. That turned out purple, so this must be alpha RGB. Alright, so to test that, and remember our blit 32 bits per pixel bitmap function is currently, it doesn't take into account alpha at all, so wait, yes it does. I don't know what we're doing. Alright, let's see if let's see what color that is. Alright, that's red. This then should be green. And it is very green. Okay. So then that will be blue. Whoops. Stop clicking on things. So it's blue. Alright. There we go. So now it's, so it's ARGB in that order. So that is why we actually don't need that clear screen function as we've written it at all. And that's also why the memset operation, even if you tried to use the clear screen function that we wrote that specifically uses the AVX 256-bit registers, you still will not be able to beat the performance of good old-fashioned memset, because memset is already optimized to use all these tricks and things that go really fast. So, all right. So I guess we'll need to make this black. And at least I know over this, since our back buffer is relatively small, you can't tell any difference between memset and cont'd. Even though, if you think about this game drawing area memory size divided by size of pixel, you think that would lead to us performing 25% as many operations. You don't really see any performance difference between those two, I don't think. So I wouldn't worry about it. Okay. So with that being said, I'm gonna leave the SIMD and AVX stuff in there for now, because we might come back to it later when we do alpha blending. If we do alpha blending, but if it turns out that we don't need it, then we'll rip it out. So let's go ahead and delete that. Alright, improve variable names with global sound effects. Let's go do that. Let's find game sound. I don't like the underscores. And effectively, the reason I'm changing the names of all these is simply because they weren't descriptive enough for me. Like, I couldn't read G menu navigate and immediately know that that variable was a sound. It might be something else other than a sound. So I just wanted to make the variable names more descriptive here, so that you could actually tell just by looking that the variable that you're looking at is in fact a sound. Okay. And speaking of sound, I suppose I should change my speakers, turn my speakers back on. Okay. It's looking pretty good. Let's go back to title screen. And we forgot to, we need to reset our local frame counter here. Remember, this is the block of code where we have exited this state, this game state at some point, and then we've re-entered it at some point. And this is how we know it's because the total number of frames rendered has somehow gone beyond the last frame that we saw locally here in this on the title screen. So that means that we've come back to it at some point. Okay. There we go. There we go. Okay. White. So I think we basically want to take this and we want to make it exactly like the splash screen. So we're going to change this to a static pixel called text color, just like we have on the splash screen. And we're going to get these variables in the same order in which they appear on the splash screen. Local frame counter, last frame seen, text color. Fine. We're effectively just going to do what this does, only in the opposite direction, because we're fading in, so we're going to gradually make the text brighter. Okay, and if we're effectively just reversing all these things, because we're going to fade in at the beginning of the game state as opposed to fading out at the end of the game state. This part is irrelevant. And my logic here is basically if we're between 180 and 210 frames, and that is of course in our local frame counter, and our local frame counter is some multiple of 15. And I'm sure if you're still watching this, you probably already know what this is, but this is modular arithmetic, and it basically means that local frame counter divided by 15 is going to have some remainder. And if that remainder is 0, then this evaluates to true. And what that has the effect of basically saying, I want this to occur on every 15th frame, on every multiple of 15 frames. Only this time, actually, we're going to start, let's start with black. And every 15 frames, we're going to add 64 pixels of color to it, until we get to frame 225, at which point we're just going to turn the text completely white. And we need to change this to text color. Text color. All right, let's see what that looks like. Well, it doesn't look very good at all, does it? That did not work. Let me get rid of these. Yeah, my logic was obviously my logic here is obviously quite flawed. All right, that's not right either. What you saw there was us cycling through, going. We were basically wrapping around because it's only an 8-bit. We only have 8 bits for each color channel, so 255 or 0xFF is like the maximum number that we can get to, right? So in a uint 8. Right. So once we pass that, we wrap around, and then the text is dark again. So this was obviously a big fail. This was dumb. So it's effectively, let's try this again. We could just say that we want this whole. Let's just do this the easy way. We'll make it fancier later, but for now, here's what we're gonna do. And of course, you can make this fade smoother if you wanted to do it more frequently than every 15 frames. If you wanted to increment it by less than or fewer than 64 pixels every time. But this way we'll have a transition that lasts 1 second, which is pretty nice. What's 128 plus 64? 192. Okay, let's see what that looks like. Okay, this fades out, and that fades in. Looks pretty good to me. Now here's something interesting. If I go to the options screen, of course, will need the same thing. But now I'm going to move from the options screen back to the title screen. I wonder what will happen. What happened is that we forgot to reset the pixel in the case that we re-enter the scene, re-enter the game state. We need to reset the pixel. Alright, let's see what happens. Fade in, go to options screen. There we go. Very nice fade. Alright, let's go to... We need to go to the options screen, and we need... Actually, before we go there, we need to go and we need to fix the screen size thing. And I think I added something off camera to the game perf data structure. I think. Or was it off screen or no? I added these last time on last episode. Where now instead of just a monitor width and a monitor height, now we have a window width and a window height. And we are going to basically go to the create main game window function, and we are going to, that's where we're going to mess with these things. If you recall, in the load registry parameters function is where we read those things. And if they don't exist, then they default to 0. Let me find this log file. Right, so if the registry for window width and window height is not found, then it uses a default of 0. So we're going to say, we're going to go back to create main game window. And we're going to go, okay. We're going to say if g performance data dot window width equals 0, that means that we are at the default, and we are going to replace that with dot window width. We're going to replace that with g performance data dot window height. And the same thing goes for monitor width, obviously. Performance data dot if window height equals 0, then g performance data dot window height equals g. Oh, I already messed it up. G performance data dot monitor height, and this needs to be changed to monitor width. Okay, so if the window width and window height are at their defaults of 0, then we are going to replace them with, we're going to make them the size of the full monitor width and monitor height. Now, instead of in the case that window size is smaller than monitor size, this is an issue because I don't know where to place the window. If the window height equals monitor height, if those are the same, if those are the same, then we'll do that. You know what? Scratch that. Scratch that. We'll just leave that as is. But this needs to be set to window width and window height. Now, somewhere in here, before we start, say if, now if if window height is greater than monitor height, and I'll give you a perfect example of when this can happen is if you have a laptop and a docking station and you play the game on while the laptop is docked on a docking station and you calculate the monitor width at that point, then you have a larger monitor because you're playing it at the docking station with large monitors. And then you undock the laptop, start the game again. What's going to happen is that you have a much smaller laptop with a smaller resolution on the laptop. So the calculation is going to be wrong. The window size is going to be larger than the monitor. So we're going to have to fix that. And then if you then dock the laptop back in, we're going to have a situation where, well, let's just stick with that. When you undock the laptop with the smaller screen, we're going to have issues here. In situations where window height could be something like 1440, and then I unplugged the laptop, and now my real monitor height is something like 1080, for example. So we're going to have to compensate for those sorts of things. So let's see, if window height is greater than monitor height, or window width is greater than alright, so if either of those things, if it's larger than, we better log it. Say the window width or window height retrieved from the registry was larger than the current monitor size. Alright, so at this point we're simply just going to reset them because the monitor width and the monitor height are sort of the ultimate like they have the final say, right? The window can never be larger than the monitor. I mean, it can technically, but it won't be able to fit on the monitor, and what is the point of that? So we don't want that. Now, before we leave this function, I think we need to decide on sort of a minimum and maximum size. So if I go to true 16:9 resolutions, so we know that the resolution of this game is 384 by 240, which is not correct. What is the size of this game? Oh. Yeah, I think I just came to an unfortunate realization that we do not have a 16:9 resolution. 384 by 240. Interesting. It's not 16:9, but it is a multiple of 16. So I think I'm going to stick with it. So what I'm thinking right now is that since this is not a 16:9 resolution, or since our game is not at a 16:9 resolution, then I really don't think I don't really think I should be running my game at full screen on my monitor either, because my monitor is 16:9, and I don't think the aspect ratio looks correct. So I don't want to change this resolution yet at this point. I want to try to stick with that resolution, but we need to figure this out. What we're going to do is we're gonna okay. I did not see this coming. I feel like if we go back down to perf data, our perf data structure, we should probably have a max scale factor, as well as a current scale factor. So what I mean by what does scale factor mean? What does that mean? I mean basically a scale factor of 1 is going to be 384 by 240. It's going to be the same as our game's resolution, which means that that would make a very tiny window in the center. And it's such a small window that no one is ever going to want to play at that size. But let's just leave it at that. Whereas a scale factor of 2 will be 384 times 2 by 240 times 2, right? So basically we're going to have to figure out what is the largest scale factor that we can have without creating a window that is larger than the monitor. And then the current scale factor will be in case the user wants the window to be smaller for some reason. So let's see. Let's do I'm just picking 12 arbitrarily because I don't think that this game would look very good at such a large resolution. 384 times 12. So someone would need something larger than a 4K monitor, and I don't think I know that they have those 32-inch like ultra wide monitors that sort of like are curved, and they offer like this really wide, really wide screen. That's not applicable to us at all. We want a pretty small window compared to that. We're not going to stretch all the way across a monitor like that. And you know what? It's good that we're doing this because this game, this resolution and window size, as we had it configured, where we just assume that it's going to take up the entire monitor. That was a naive assumption on our part. So it's good that we're getting this out of the way now, because someone could have one of those 32-inch monitors like that, where it's it's like it's like this wide, and you don't want the game taking up all that real estate, because not only does it cover up all of this other stuff on their monitor, but it's going to look terrible. Your character would be like a pancake. He'd be like this wide and this long. No, it'd be stupid. All right, so we'll say if let's say if game res width times counter. Suppose we should start at 1, because our scale factor is never going to be 0, because that would make our resolution 0, right? Is greater than max scale factor equals counter minus 1, right? Because once we've reached, if resolution times counter is greater than the size of our monitor, that means that we've already gone past the size that is acceptable, so we're going to step back 1. That's why we're doing counter minus 1 here. Except I've got to make sure that these stay consistent. I was comparing height to width there. That wouldn't have been good. That would have been a bug. And now we're still going to potentially run into an issue with people who orient their monitors vertically. You know, some people turn their monitors on their sides. That could still be an issue. It would be a lot easier if I had these sorts of hardware configurations to test with, but I don't. So I'm just going to have to imagine and let's go ahead and add a break there. Once we got what we came for, we can break out of the for loop. Okay. And let's go ahead and set current scale factor to max scale factor. We'll probably have to come back to this in case the users resize the window. But I want to go to our good old render frame graphics function. Scroll down here a bit to, oh, you know what, all this can be, we can whack all of that. We don't need any of that. All right, stretch DI bits. So since we're no longer committed to drawing this, stretching this canvas all the way across the entire screen, we need to come up with something else. So I think we're, I guess, just going to Maybe I'll just draw it in the center of the screen for now. And these need to change. What is this? Dist width, dist height, source width. Actually, these need to be here. Okay, this is X destination and Y destination will be center screen. And these are going to be current system time. Awesome. Okay, 0, 0, width and height, all that stuff is good. Alright, I guess let's just see what it looks like first. Build errors. Oh yes, we need a log level. Log level info. So the end result is this is actually quite a pleasant end result in my opinion, because what we have achieved here is that we are basically now drawing the game as large as we possibly can on this monitor without blowing out the 384 by 240 aspect ratio, right? Since we were never actually at a 16:9 resolution, it wouldn't make sense to cover the entire monitor because I have a 16:9 aspect ratio monitor. So that would actually mess up. That was actually making all of my graphics a little stretched out, a little wider than they actually should have been, which is exactly what I want. So this pink stuff, these pink borders, are from that's the window. That's the part of the window where the back buffer is not. It makes sense? Remember at the very beginning, oh, and I'll go ahead and show you. In Create Main Game Window, if I go up here, this is something else that I changed while you weren't looking. If I'm compiling in debug mode, then I create the background of my window with a hideous purple color. And remember, full R and full B make for purple. But if I'm compiling in release mode, then I just paint it black, so it's not a hideous pink color. The hideous purple color helps us find bugs during development. So yeah, that part went pretty well. Now I think I'm probably over an hour, or I'm right about at an hour. I'm just wondering. I'm thinking I probably don't want the bars though. Is the thing. In render frame graphics, I centered the back buffer into the window. Window. Yeah, but I think I would actually like to do without the. I don't want the pink bars on the side, or the black bars if I'm running in release mode. See there? It's the same effect, only the window is now the same color as the color that I'm painting the back buffer, which is black. Alright, so I'm going to go ahead and stop here because I know we are at an hour. So we're going to stop here. We're going to pick up next time by finishing this. We're going to, let me go ahead and write up here what our plan of attack is going to be. We still need to save these things to the registry. I want to get to a shadow effect for the text. That would be cool. What we're going to do is, next time, we are going to finish the customizable window size in the options screen. Okay, and where are we going to go from there? We are going to go to a character naming screen from there, which is essentially, you know how almost all those old Nintendo games, they allowed you the ability to name your own character, and you would name him things like ass and whatever other bad words your 8-year-old brain could come up with. You're going to be able to name your own character, and then finally it will drop you into the overworld where you can pilot your little character around the screen again. And after that, we're going to introduce a whole new concept of tile maps, and then we need to introduce Vorbis background music, and then we need to introduce I think we're going to introduce some sort of like archive format for game assets. And the idea behind that is, we've been loading all these bitmaps and WAV files directly from the disk. But what video game have you ever seen that ships like that? The answer is none. None of them do. If you think back to Doom, pretty much everyone has played Doom, right? The assets, all of the maps and the textures and stuff, they would be packed into a file that was named something .wad, W-A-D. So we're going to do something like that, where we take all of our WAV files and all of our BMP, all of our bitmap files and all of our whatever, and stuff them into a compressed archive. So then we're going to have the benefits of having data compression, so our game won't take up as much space on disk, and then we'll also have the benefit of, people can't go in there and just easily edit your game assets and make the game look like whatever they want it to look like. It'll still be possible, just harder, you know. So it keeps people from doing it unless they really know what they're doing. Anyway, I think that's it for today. I'm going to call it. And as always, thank you very much for watching. Please like and subscribe if you would like to continue development on this game. Don't hesitate to leave any comments or questions on the YouTube videos. If you have any comments or questions about any of the stuff that you've seen in any of these episodes, I will address your questions in one of these upcoming episodes. Also, don't forget to clone the companion GitHub repository. There is a GitHub repo that goes along with this that you can download just so that you can code along with us and from the comfort of your own home. So with that, I bid you adieu. Until next time. Thanks. Bye.